Students who've taken a pre-calculus course often have no idea what an elementary function is or how elementary functions are classified. It's a case of getting lost in the forest, not being able to see the forest for the trees. Okay, so constant function f of x equals c, one of our, very basic function, very simple function. There's nothing much you can do with that one except add it to other functions. Okay, linear function, f of x equals x. The most basic linear function is f of x equals x. Now we can generalize that function. If we multiply x by a, which corresponds to vertically stretching the function by factor a, we can manipulate the slope. A will be the slope. If we then add b to the function, well, that corresponds to vertical shift by amount b. We can get the function to have any slope with a, and we can move it to any position on the plane. So we can get any linear function just by the two parameters a and b, by adjusting these two parameters. By the familiar, or what should be familiar process of horizontal stretches, horizontal shifts, vertical shifts. In the case of a linear function, only a vertical stretch and a vertical shift. Okay, and we think vertical shift, we could do the same thing with a horizontal shift, but the b parameter would be a vertical shift. Okay, power function, f of x equals x to the p. Simple example, f of x equals x squared, or if you like, x cubed, or x to the negative 1, which would be 1 over x. All kinds of different power functions, some with characteristics that are quite a bit different than others, and some with similar characteristics. We generalize the power function using a vertical stretch by factor a horizontal shift h, and a vertical shift k, and we can then transform this function into any desired function that's based on the power p. Okay, so we get the generalized power function. Okay, quadratic functions and polynomial functions are just instances of where we add multiples of power functions together. Quadratic function, we add a multiple of x squared, which is a p equals 2 power, x, which is the p equals 1 power, and 1, which is the p equals 0 power, x to the 0 being equal to 1. And we can get any function we wish. The most basic function is f of x equals x squared, transforming f of x equals x squared by a vertical stretch, a horizontal shift, and a vertical shift. We get this vertex form, it turns out, of the quadratic, and of course we can expand this and get it in the form ax squared plus bx plus c. And given a form ax squared plus bx plus c, we can complete the square, bring it back into this form, and see what the vertex and the vertical shift are. Exponential function, the most basic exponential function might be f of x equals b to the x, where b could be any non-negative number. The most natural exponential function is f of x equals e to the x, where e is the limiting value of the quantity 1 plus 1 over n raised to the nth power as n approaches infinity. These are easily connected. If we understand logarithms, we can easily do this. Of course, we need to understand exponential functions before we understand logarithms. Generalized exponential function could be a b to the x plus c. That's three parameters, a, b, and c. Or using the natural base for the exponential function, a e to the kx plus c, with parameters a, k, and c. This form is the same as this form, as long as, and you can show this easily if you understand the laws of exponents, okay, this form is the same as this form as long as b equals e to the k. Or if we know b and want to find k, k is going to be the natural log of b. The logarithmic functions are inverse to the exponential functions, base b log being inverse to the b to the x exponential, natural log being inverse to the e to the x exponential. And inverse simply means that if you apply the log base b to the b to the x function, you just get the identity function x, or apply the natural log to the natural exponential natural log of e to the x. Again, you just get the identity function x. The trigonometric functions. Okay, you have f of x equals sine x, f of x equals cosine x, f of x equals tangent x. Just looking at the sine function, we generalize by a vertical stretch by factor a horizontal compression by factor b, a vertical shift h, and a horizontal shift h and a vertical shift k. That's 4 parameters. We can take the sine function, our nice wavy sine function, and we can compress it like an accordion or stretch it out as far as we want. We can make it wider or narrower in this direction, changing what we call the amplitude. We can shift it right or left, and we can shift it up or down with these 4 parameters. And we also have the inverse trigonometric functions that are defined by inverse relationships, very much like this. In other words, the inverse sine of the sine of x is x. And that there are issues related to the domains of these that I'm not going to talk about. You have to restrict the domain of the inverse function, but within that restriction, what I just said is so. And we don't typically generalize these. We mostly use these in solutions of trigonometric equations. Now, there are a couple of other functions that I've listed. The floor and ceiling functions. The floor of x is the greatest integer that's less than x. The ceiling of x is the smallest integer that's greater than x. These are important functions. They're not really elementary functions. They're not basic elementary functions, nor is the absolute value, but it's an important function. It can be generalized with the same parameters we use for a power function or quadratic function or whatever. Absolute value is really a split definition function of 2 linear functions. So it's not really a basic function. Okay. Polynomial functions are obtained by adding power functions. They're not basic functions, but they result directly from the arithmetic operations on the power functions. If we then allow combinations of these functions, if we combine these functions by multiplying them, adding them, composing them, doing a composition. Okay, for example, if we multiply an exponential by a sine function, we can get a sine function that kind of decreases its amplitude. That's very important for modeling a lot of oscillatory behaviors. Okay, we can combine an exponential with a power function. If we combine, take the power function x squared, take its negative, and then do a composite so that we get e to the negative x squared, actually e to the negative x squared over 2, we get the normal curve function. Okay, many ways to combine these functions. All those combinations lead us to almost all the functions that you see in undergraduate mathematics. Now, there are some other functions when you get late into differential equations course, which is a course that follows a 4th semester, or that comes in the usually 4th semester of a calculus sequence. You get some functions that are defined by differential equations, and they're extremely important for a lot of applications. But the elementary functions, very important classification of functions, very important to understand these classifications and how the functions arise. One more mention, a polynomial function can be expressed as a series of powers, of integer powers, positive integer powers, multiples of powers, multiples of integer powers. And we add those together to get a polynomial function. And any polynomial function, it turns out, can be expressed as a product of quadratic functions. And these are not only quadratic functions, they're quadratic functions that have no real zeros, irreducible quadratic functions, and linear functions. Also, we have the rational functions, functions that are polynomial divided by polynomial. All these functions would be regarded as general elementary functions, and all combinations of these functions as general elementary functions.